Okay, so welcome everyone to lecture 10, and let us continue with the theme of solving partial differential equations. So, right, so last time we saw how to solve this equation, right? Ut is equal to k square uxx and u0t, sorry. These were the Dirichlet boundary conditions is equal to 0 and ux comma 0 is equal to f of x. So last time we saw how to solve this differential equation. So today we will do something more complicated, and we are going to solve this equation. This is obviously much more complicated. So this is non-homogeneous because we have a f of x over here. That's the reason why it is called non-homogeneous. So so the homogeneous ones are of this type. So an equation of this type is called homogeneous. Anyway, the name is not very important. So let's go ahead. So how do we solve this? So we first make a substitution. Okay, we want to make these two 0. Right? So we make a substitution. Z of x comma t is equal to u of x comma t minus 1 minus x by L f1t minus x by L f2t. All right. So since we know f1 and f2, Z and u completely determine each other. Okay. And when we compute zt minus k square zxx, we are going to get some function g of x comma t, right? So yeah. So g is going to be some function. G is some function in terms of f, f1 and f2, right? And when we put z 0 comma t, when we put x equal to 0, so this 0 0, this term vanishes, and x equal to 0, so this u of 0 comma t minus f1t, and that is 0, right? So z0t satisfies this condition. Similarly, zlt satisfies this condition, and zx comma 0 is going to be some g of x, which is some g of x is some function of, I mean, I don't know, some yeah, in terms of f of x, I suppose. So let's see, let's put t equal to 0. So it's ux0 minus f10 into this thing, minus, yeah. So zx, let me not write sum, this maybe, right? So zx0 is equal to g of x, and g of x is equal to ux0, that's f of x, minus 1 minus x by L into f1 of 0 minus x by L into f2 of 0. Okay, so we have solved by using this simple substitution. We have reduced this problem to this problem. I hope this is clear. If let's just pause for a few seconds, and if you have any questions, please feel free to ask. Okay, so let's go ahead. So it is clear that we would have solved for u if and only if we have solved for z. So in view of this observation, let us try and solve the problem for z. So by observing the boundary conditions, we guess that we should try and look for a solution of the type zxt is like a bit like our separation of variables. We is some znt times sine n pi x by L. So by the boundary conditions, we are looking at these two conditions. Okay, so our aim is, okay, let's just try and see if there is a solution of this type. That's just our guess. Okay, and why do we look for sine n pi x by L? Because we want z0t to be 0. and Z LT to be 0. Because of this reason, we look for this, we put this sign. Okay. So differentiating term by term, we see that we get that it satisfies the equation. So yeah, so we just, as always, we are going to ignore about any statements about mathematical rigor. We're just going to pretend as if we can differentiate under the integral sign. I mean, under the summation sign. So that means ZT is equal to summation n greater than equal to 1 Zn prime t into sine n pi x by x. Right. So yeah, so similarly we compute zxx, and yeah, so this is going to be this thing. Okay, so this is just a straightforward check. There's nothing happening over here. We just differentiate under the, yeah, we just differentiate. Okay, so this gxt, yeah, so this gxt was this function, right? Gxt is this function. Okay, so what do I mean by this? So right, so this GNTs, these are the Fourier coefficients, but now these are functions of t. So in other words, what you can do is we can fix a t naught. We can think, one way to think of it is like this. Once we fix a t naught, then gx comma t naught, this is a function of x, and therefore it has a Fourier expansion. Some, I don't know, some an sine n pi x by l. Okay, and then the value of gn t naught is defined to be this an. Okay, I hope this is clear. So our another way of saying this is that right, by orthogonality, this g and t is going to be integral 0 to L. There's going to be some factor over here into gx comma t and sine n pi x by L, sine n pi x by L dx. Right, there's going to be a factor of, I don't know, 2 by L or whatever, the one which usually comes. So we are integrating out the x, so therefore this remaining thing will be a function of t, and that is our g and t. Okay. So thus, if we need that zt minus k square zxx is equal to gx comma t, then we should have that. So let's look at this now. We want this, so the equation we want is that these two should be equal. Zt minus k square zxx should be equal to gxt. Right, that's the equation. Zt, that is what we had reduced our equation to. So if we want these two to be equal, if we want this equality to happen, then we need that these Fourier coefficients should be equal, right? Which means that we should have this g and t. This, remember, is equal to whatever factor times integral 0 to L g of x comma t sine n pi x by L dx. Right. So, and we also need that zx0, that's our condition over here, this condition. We need that zx0 is equal to g of x. So, so if we write the Fourier sine series of g of x, then we should have Zn0 is equal to b of n. So let's see why is that. Yeah, so when we put zx0, zx comma 0, that's equal to summation n greater than equal to 1 Zn0 into sine n pi x by L. And we want this thing to be equal to g of x, right? Which means the Zn0 is the nth coefficient in the Fourier sine series of g of x. And that's what I've written over here. So therefore we get this condition. So we have Zn0 at 0 is Bn, and Zn satisfies this differential equation. Right? And clearly we know that there is a unique solution to this differential equation. There is a first order differential equation in T. We have specified the initial condition. So there's a unique solution to this. In fact, the solution is given by this. Right? And C, I mean, C is in fact exactly Zn0, right? Because C is, yeah, when we put T equal to 0, we want Zn0, which is An, the Fourier, nth Fourier coefficient of. So when we put T equal to 0, this thing vanishes, this becomes 1. So C is exactly equal to An, where I have written g of x is equal to summation n greater than equal to 1, An sine n pi x by L. Okay. Thus, we let Z and T be this unique solution. Then the series, this series solves our non-homogeneous PD with Dirichlet boundary conditions for Z. So this is the series. This series solves our equation ZT minus K square ZXX is equal to G Z0 comma T is 0, ZL comma T is 0, and Zx comma 0 is equal to G of x. Right? And then using this, we can solve for U, our original differential equation. So let's just pause here for a few minutes, and I just want to make sure that the steps are clear. So if you have any doubts, you can ask me. So the fact that this this is a solution to this differential equation with this initial condition. Okay, so I'm sorry, I should have written Bn, not An, using my notation. Okay, yeah, this Bn. Yeah, that is something which you should have learned in your MA 108. Okay, so let's see an example. We are considering the following PD. Okay, so I've made my life easy over here by taking U0t to be 0 and U1t also to be 0. So from the boundary conditions, it is clear that we should look for a solution in terms of Fourier sine series. So this is my f of x comma t. Right? And here there's no, because here my f1 and f2 are 0. Right? So my f is equal to my g in the notation I used earlier. So yeah, so we should look for, and the Fourier sine series is given like this. Right, yeah, so this is the coefficient which is 2 by L. So L over here is 1. Okay, so let me go to the next slide. So that's the Fourier sine series for e to the power t is given like this. So this is, right? These are the Fourier coefficients. Oh, I see. Oh, this function is particularly simple because this is just a function of t. So basically, we are just writing the Fourier series of 1, n greater than equal to 1, the Fourier series of 1 sine n pi x, and we are multiplying everything with e to the power t. So this is a very particularly simple function. Okay, but it doesn't matter. Okay, so let me go ahead. And the Fourier sine series for f of x is equal to x into x minus 1 is given by this. So this is something which we would have already computed at some point of time. So substitute, okay, so substitute uxt is equal to, so we are looking for a series solution. So we substitute this into the equation ut minus uxx is equal to e to the power t, and we get this equation. So that means we have to equate this coefficient with this coefficient. So we have, right, so we have so let's see. Okay, that's for n greater than equal to 1 and even, right? So when n is even, this coefficient becomes 0. When n is even, this coefficient becomes 0. So that is what I've written over here. We have this differential equation. So that is, we have this. This is our solution for u and t. And if n is greater than equal to 1 and even, we have that the Fourier coefficient of x into x minus 1 is 0. Okay. Thus, so let's look at that. Yeah, so when n is even, this Fourier coefficient is 0. So thus, if we put un 0 equal to 0, we get Cn is 0. So it means all the uns are 0 for n even. For n odd, when we look at this, yeah, for n odd, we look at this once again, and we have this differential equation, which means our unt is this for n odd. Okay, and the Fourier coefficient, and if n is greater than equal to 1 and odd, we have the Fourier coefficient of x into x minus 1 is this thing. Thus, we get un0 is equal to Cn is exactly this thing. This, as I had remarked earlier. So therefore, the solution we are looking for is here. So there's n greater than equal to 1, and only odd terms appear because there's 2n plus 1 over here. And there's 2n plus 1 pi. So you can verify the details earlier, but the point is that you should have understood the main steps. So if you have any questions, you can ask me now. I think this is the only example here. So I'm going to paste the details of the Zoom meeting link which you have to join. Because of some license issues, there's a chance that this meeting may end after 40 minutes. So yeah, we will join at this new meeting link, which has been entered in chat. So I hope people will be able to join. Yeah. Okay, so let's go ahead. Since there are no doubts. So let's look at, so once again, we are going to go through the whole process again with Neumann boundary conditions. So by Neumann boundary conditions, we mean that ux, there's this extra x over here. These conditions are on the derivative with respect to x. And if you, so yeah, when we go over this example, the idea will perhaps become clarified once again. So as before, we make a substitution. Zxt is equal to, we make a substitution to get rid of these boundary conditions. These two. So zx comma t is equal to uxt minus, yeah. So you can easily check that these two conditions will happen. And this g is going to be some function in terms of f, f1 and f2. Right, and what is gx going to be? Gx is going to be f of x minus, yeah, exactly, 2l into f1 0 minus x square by 2l into f2 0. Right, and as before, z and u completely determine each other. So solving this set of equations is equivalent to solving this set of equations. So we will solve the second set of equations. And it is clear that we would have solved for u if and only if we have solved for z. So in view of this observation, let us try to solve the problem for z. And once again, by observing the boundary conditions, these two conditions, right? This condition and this condition, we are taking the derivative with respect to x over here. So we would like to look, it is our guess that we should solve, look at a series of this type. Right? So let's compute, we differentiate term by term, and when we look at zt minus k square zxx, we get this thing times cos n pi x. And this thing should be equal to g of x comma t, right? But now we can write the Fourier cosine series of g of x comma t. We write it as g n t times cos n pi x by l. Right, where g n t is the g n t is integral 0 to L with the correct coefficient g into cos n pi x by L dx. We just integrate out the x, so what remains is going to be a function of t. Okay, for some reason Zoom has removed the 40-minute restriction on this meeting, so we can continue. Yeah, Zoom has gifted it to me. Okay, great. So yeah, thanks to Zoom, there won't be any interruption in a beautiful analysis of differential equations. Okay, so let's go ahead. So we want these coefficients to be equal, right? This should be equal to g and t. So this g is given to us. Therefore, we know these Fourier coefficients g and t, which are by definition these things given by this integral. So yeah, so let's write g is this thing, and So therefore, if we need, yeah, so then we have to have that the Fourier coefficients have to be equal. These two have to be equal. Okay. So we have this differential equation. And once again, we need that zx0 is equal to g of x. So if we write the Fourier cosine series of g of x, then, right, so we want this to be equal to z of x comma 0, which is equal to summation n greater than equal to 0, zn 0 times cos n pi x by l. Therefore, this zn 0 has to be equal to this Bn. And once again, we have, this is a differential equation, first order differential equation in one variable. We have specified the initial condition. This has a unique solution, right? And this is the solution. And the C is exactly Zn 0, so it's equal to Bn. So thus we let Zn t be the unique solution, then the series Zxt solves our non-homogeneous PD with Dirichlet boundary conditions for Z, and from this we can recover U. And from this we can recover U or find the solution for our initial differential equation. So let me once again pause here. The steps are fairly straightforward, and if you have any doubts, you can ask me. Oh, thank you very much for this reminder, but we don't need the reminder we don't need to move anymore because Zoom just gifted us 40 more minutes for this meeting. Yeah, but if for some reason this meeting shuts down, then I will move to the other meeting. The link to which has already been given in chat. Okay, so if there are no questions, in the last line, should it be Neumann condition? Oh yeah, I'm sorry. Thank you very much. This should be Neumann condition. Neumann boundary condition. Thank you very much. So let's move to an example. And the example is going to be, okay, it's the same example. So yeah, with the same functions. So except that these two conditions have changed because here we have an additional x. So once again, here life is simpler for us because, yeah, I mean, so we don't need a substitution in this case, right? So from the boundary conditions, it's clear that we should look for solution in terms of Fourier cosine series. So we compute this is our f of xt. So we compute the Fourier cosine series of this. So that's just the Fourier cosine series. This is not a function of x in any way. So this is just going to be the Fourier cosine series of 1 multiplied with e to the power t. So yeah, so that's this thing. Okay. Oh, wow. Oh, yeah. Right. Because The Fourier cosine series, right? The Fourier cosine series for 1 is just 1, right? Because we know that the eigenfunctions are 1 and cos n pi x by L for n greater than equal to 1, right? So therefore, yeah, I mean, you can of course compute this integral and that will turn out to be 0 if n is strictly greater than 0. But we could have said it directly also. Yeah, that makes life easy. So the Fourier series for e to the power t is simply e to the power t. The Fourier cosine series is something which you would have computed earlier, is given by this. Okay, so when we so this is the solution that we are looking for, and we substitute this into this equation, so we get this. Right. So that means, so what do we get? For n equal to 0, we have this, right? When we put n equal to 0, this term vanishes. So we have un prime t is equal to e to the power t. And for n positive, we have, okay. Oh, okay, I've written it like this. But what about for n greater than equal to 1? Yeah. Okay, so okay, let's finish the n equal to 0 case then first. That's how I've done it. So this is actually e to the power t plus 0 times, this is the cosine series, right? 1 pi x by L plus 0 times cos 2 pi x by L and so on, right? So when, yeah, so when n equal to 0, the differential equation we get is this thing. Un prime t is equal to e to the power t. And we have the initial condition. Okay, so this is this. And in case n equal to 0, we have that the Fourier coefficient of x into x minus 1 is minus 1 upon 6. Okay. Right. So we had already seen this, right? So let's see. Let me go back. We have that Zn0 is equal to Bn, where Bn is the Fourier coefficient of g of x. G of x in our case is x into x minus, yeah, whatever it is, x minus 1, maybe x minus 1. So our u0t is of this type, and we have to compute c0. And for that, we have that u0 of 0 is equal to the Fourier coefficient, the 0th Fourier coefficient of this, which turns out to be minus 1 by 6. So when we put this, we get c equal to minus 7 by 6. So our u0 is e to the power t minus 7 by 6. And for n greater than equal to 1, this is 0. Yeah, we have this equal to 0, which means that this is the differential equation that it satisfies, and which means this. And now we can use the initial condition to determine the constants. So what does that mean? So in case n is greater than equal to 1 and odd, we have that the Fourier coefficient of x into x minus 1 is 0. So remember, we know that un0 is equal to bn, where bn is the Fourier coefficient of sorry 0, right? So okay, so anyway, you can check this. So there is a computation for, so our un for n greater than equal to 1 looks like this, and un0 is equal to bn. So yeah, this is exactly bn. Okay, so and we can get this equation. So this is the solution to our differential equation. So let's just pause here for a few minutes. And you can ask me if you have any doubts. So I have gone over this example, both examples a little bit quickly, but that's because, I mean, the example is just following the theory in a very algorithmic way. So what is important is that you should understand the steps in finding the solution. Okay, so if there are no other questions, I will stop sharing these slides and we will start our next chapter. So we will now start the wave equation. Okay. So once again, the template we will follow is, we will see how to solve the wave equation for Dirichlet boundary conditions using the method of separation of variables. Then we will see how to solve the wave equation for Neumann boundary conditions using the method of separation of variables. And finally, we will come to the non-homogeneous wave equation. And it's very similar to what we have done before. So let's begin. So this is the wave equation. So here we have utt is equal to k square uxx, and x is between 0 and L, and t is strictly greater than 0. So, okay. And these are the initial conditions given to us. So ux, oops, sorry. So yeah, in fact, maybe I can use this. So ux0 is equal to f of x, and ut x comma 0 is g of x. So this is the t derivative of u. So, and we also have some boundary conditions. u0t is equal to ult is equal to 0. So basically we are given this as 0 and L, and we are given our wave. This is, yeah, at time 0, this is f of x, and we are also given the, I don't know, velocity of the wave's propagation at time 0. And we have to solve, see what the wave looks like at time t. So, okay, right? Right, so if I were to write it down precisely and, oops, sorry. Right, so the equation we have to solve is the following. utt is equal to k square uxx and u ux comma 0 is equal to f of x, ut x comma 0 is equal to g of x, right? So I think, yeah, maybe I should write these two a little bit below. And we have u 0 comma t is equal to 0, u l comma t is equal to 0. So this is the differential equation we have to solve. Right? So as in the case of the heat equation, we will use the method of separation of variables and try to find solutions to these three conditions first. Okay, so let's go ahead. So we will use the method of separation of variables to first find some solutions to the wave equation with boundary conditions. And that is, we forget about the initial conditions for now. So we assume we have a solution of the type ux t is equal to ax into bt. So substituting this into the wave equation, we get this, utt is equal to k square uxx, we get this. That's immediate. And we separate the variables. So the equality is between a function of x and a function of t, so both must be constant. Let's say minus lambda. And therefore we get these two conditions. And we also have this boundary conditions, right? So now the whole process repeats. So since we don't want b of t to be identically 0, we get a of 0 should be 0 and a of l should be 0. So we solve this eigenvalue problem, this one, along with these two conditions. Right? So the eigenvalues and eigenfunctions are, so the eigenvalues are lambda n is equal to n square pi square by L square, and the eigenfunctions corresponding to this eigenvalue is an is equal to sine n pi x by L. Right. And for each lambda n, so we have, so these are the only possible lambda n's for which we have non-zero solutions for the ans, and for each of these we will solve this equation. Right. So what do we get? So for each, right, so for each lambda n we get a solution for b given by b and t is equal to, right. So remember that this equation, for this equation, since there are no conditions on the boundary, the eigenspaces were two-dimensional. They were generated by cos and sine. Right. So I mean, I could have written alpha n cos this thing plus beta n sine this thing, but instead of that, I will write my beta n's like this. Okay. So thus, uh, thus we get a solution for each n greater than or equal to 1. This solution is, I'm sorry, just 1 second. Sorry. I'm really sorry about that. So, okay. So for each n, we get a solution u n x t is equal to b n t times a n x. So that's of this type. Right? And we are looking for a series solution of the type u x t is equal to summation n greater than or equal to 1, this u n x comma t. This is exactly what we, or not exactly, what we did earlier was very similar to this, right? Right. So now, when we have the boundary, conditions, ux0 is something and utx0 is something. So, right. So when we put t equal to 0, yeah, so this term vanishes and we just get alpha. Yeah. And this we want it to be f of x, and this we want it to be g of x. Right. So alpha n and beta n are determined as the Fourier coefficients of f of x and g of x. Okay, great. So, yeah. So let me just go to the slide which gives the final solution. So let f and g be continuous and piecewise smooth functions on 0L. So that f of 0 is equal to f of L is equal to 0. So that's because we want our wave to be, right? We want our wave to be of this type, this 0 and this L. This is the position of the wave is given by f of x. And, right, and we want, this is the differential equation we want to solve. Right, so this has a solution which is given like this, where alpha n's are this and beta n's are this. So if people have any questions, they can ask me. Okay, if there are no questions, then let's see an example. So consider the wave equation with initial and boundary conditions given by this. Okay. So here I've made life a little bit easier by cheating. I mean, cheating in the sense I have given my functions ux0 and utx0 already in a Fourier series form. Right? I mean, if you have a function of this type, then the Fourier series is obviously computed trivially. I mean, the Fourier, because, yeah. Okay. So since both f and g are given by their Fourier series in your example, it is clear that alpha 1 is equal to 1. So these are the Fourier coefficients of f. Fourier sine series coefficients of f. So this is my f, right? And there is my g. And these are Fourier sines. And all the other coefficients are 0. And these are the Fourier sine series coefficients of g. Okay. So thus the solution to the above problem is given by this. It's simply this. Right. So we just go to the previous slide here. So we have to compute the alpha n's and the beta n's. So these are the Fourier coefficients of f and g. And we just have to put this into this. Okay, so our alpha n's and beta n's are given like this, and all the others are 0. Right, so in the first one, only alpha 1 will occur, and alpha 1 is 1, beta 1 is 0. In the second one, both alpha 5 and beta 5 will occur, and then there's going to be an alpha 9 where only beta 9 occurs. So that's exactly this. So this is the 3, I suppose. So this 3 is this 3, and this beta 5 is, there's a 1 over here. So remember that so here we had a L and pi. Okay. Okay, I'm a little bit confused. Why is there a square root 5? Have I made some mistake? Okay, I'm a little bit confused because I don't know why there is a square root 5. So I'll just check this. 5 is equal to k square. Oh, okay, thank you. Thank you very much. Yeah, you're right. So there is a k, right, there's a k over here which is giving the, thank you very much. Yeah. Yeah. Yeah, I'm sorry about that. So in the exam, your questions will be like this, okay? I mean, I'm not going to ask some painful question where you have to compute some, right? Okay. So, and once again, so let's just analyze the Neumann boundary conditions as well. So this time, right? So we have this. So we will use the method of separation of variables. We will look at this along with these two first, right? Right. So we put ux comma t is equal to ax bt. We put this into this differential equation and we get this, and we do all the same things. Right. And then we have this. Right. But now, since we are over here, we have this a dash 0 and a dash l should be 0. Right. So we first have to solve this problem. Right. So we have this eigenvalue problem. A double dash x plus lambda a of x is equal to 0, and a dash 0 is equal to a dash l is equal to 0. So, and the only eigenvalues are lambda n is equal to n square pi square by l square, and a and x is equal to this thing. And then for each value of lambda n, we will solve this one. P double dash t plus k square lambda pt is 0. So for each, we have this thing. And now for n equal to 0, we get this solution. Because for n, when we put n equal to 0, our lambda n becomes 0, and this will just be 0. And for n greater than equal to 0, I'm sorry, n greater than equal to 1, we have this solution. I mean, we write our beta n's like this. So therefore, for each n, okay, so for each n greater than equal to 1, we get a solution of this type. And for n equal to 0, we get a0 times b0. So n equal to 0, we get pn b0 t times a0 x is just going to be equal to beta 0 t plus alpha 0. Because a0 x is just the constant. Okay. Yeah, okay, I've written it here. So from the above, we conclude that one possible solution of the wave equation is the, yeah, so we are going to put together all these. We are going to put together all these. We are going to look for a solution of the type uxt is equal to summation n greater than equal to 0 un x comma t. Right, so we have this. And then we are going to put in our boundary conditions ux0 is equal to f of x and utx comma 0 is equal to g of x. Right, so let's see. Right. And this we want to be f of x, and this we want to be g of x. So once again, clearly, we can get the beta i's as Fourier coefficients of g of x and the alpha i's as Fourier coefficients of f of x. Right, so let me just go to this problem. So this theorem. So let f and g be continuous and piecewise smooth functions on the interval 0, L. So then we have this differential equation. This has this solution, where the alpha i's and beta i's are given like this. Are there any questions? If there are no questions, then we will see once again one very simple example, and then we will end today's class. Yeah, so the problem is, yeah, so you see, we have written a series, right? Yeah, why do we specifically say actual solution? Yeah, so the point is, I mean, we have written this series, and if you want to prove everything rigorously, then you will have to make sense. First, you will have to show that, okay, this series actually defines a nice function in our, I mean, our wave equation is defined on this 0, L cross 0 infinity, right, to real numbers. This is my x variable and this is my t variable. So you are you have written this as a series. You have written a series. So first of all, you have to make sense that okay, this series converges for each value of x of this pair. This gives a real number. Then you have to make sure that you know you can differentiate, take partial derivatives inside the sum. So you have to do all those things. So, and the question is, can we do all these things? So that's why we, yeah. But if, let's say my f and g are like nice smooth functions on the interval 0, L, then we can do all of that. I hope that answers the question. Yeah, I mean, right now we have just gone through a process and found out, written some series. The whole question is, does this actually have any physical meaning? So, yeah. But of course, in this course, we are not worried about mathematical rigor at all. Yeah. I mean, this itself is like a very big thing, because suppose you would have been given this differential equation, and you are asked to solve this, like even to write a series which will formally give the solution is an incredible thing, I think. And of course, once you write the series, once you have a candidate for for a solution, then you have to prove all sorts of nice things for your function. So let's see a simple example once again. So we are looking at this. So once again, here I have already expressed the function in terms of its Fourier cosine series, right? This is the Neumann boundary conditions. So I've already expressed the function in terms of its Fourier cosine series, which makes life very easy. Right, so these are the Fourier coefficients of f. This is my f, and this is my g. These are Fourier coefficients of g. And yeah, so we can just plug in the formula directly. Okay, so this is enough for today, I think. Maybe next time we can do the non-homogeneous wave equation. Today is only lecture 10. Yeah, so I think we need, yeah. So this is a good place to stop. If there are questions, I can address them. Otherwise, we will end today's lecture. So I will wait for 5 minutes for questions, and if there are no questions, then I will end. So did people think that the midsem, the quiz was easy? I mean, I don't know. Since there are no questions. Okay. Yeah, I thought so too. I suppose if it would have been a subjective one, I would have made it a little bit more difficult. But I guess giving an objective quiz in this course, yeah. Okay, if there are no other questions, then let's end today's class. Thank you for coming, everyone. Bye.